We can sometimes alter the speed of a reaction by using something called a catalyst. And so in this video, we're going to talk about different types of catalysts and how they work to facilitate a reaction. So our learning goals are to describe the types of catalysts that occur and how they facilitate reactions. Now, what is a catalyst? It's basically a species that facilitates a chemical reaction, but it's not consumed by the reaction. So it's there and it can keep working to facilitate the reaction many times over. It's distinct from reaction intermediates. Remember, an intermediate was something that occurred during different steps of a reaction mechanism, but the distinction is quite important. Catalysts are present at both the beginning and the end of a sequence of reactions, but you may have difficulty finding them in the middle because they're altered in their form somehow. Intermediates are almost exactly the opposite. They usually aren't present at all at the beginning and the end of the reaction. They're only present in the middle. So we're going to discuss three principal types of catalysts. There are probably some others, but these are the ones that you'll run into most often. The first are acid-base catalysts. The second are heterogeneous surface catalysts, and these are usually metals, although they can be other materials. And the third is enzymes, that is, the things that are in your cells that help your cells perform all of their reactions. Now, I'm going to describe two general mechanisms for catalysis, and again, there probably are more, but these are the ones that are going to capture most of the catalysis that one would run into. The first of these is one where a catalyst can form temporary new bonds to the reaction species. So, in other words, it interjects itself into the reaction, it forms a bond, a reaction happens, and then it lets go of the bond, releasing the products. So this is a very direct sort of involvement. A second way that a catalyst can help, though, is by providing a template for the reaction. And this means that it's creating an environment in which the reaction can take place more easily. So even though the catalyst itself doesn't get involved much in bonding with the species, it still provides the correct environment for that reaction to happen. Now, I want to look at some energy diagrams to talk about exactly what it is a catalyst does. I'm going to say right off the top that what a catalyst really does is it changes the reaction mechanism for a given reaction. So let's take the left-hand side and just say if we start off without a catalyst, our activation energy would be from the dashed line up to the top of that curve, up to where the transition state is. And that would be the energy, and we know that the energy is what helps set the reaction rate. So the higher the energy, the slower the reaction. A catalyst might change that reaction mechanism, though, to create a new activation energy that's somewhat shorter. And you'll often see pictures like this drawn in books to describe that what a catalyst does is basically provide a tunnel through that barrier that allows the reactants to go to products without going over such a high barrier. I don't like this picture so much myself because it seems to imply that the action of the catalyst is in an elementary step for a reaction, because remember, an elementary step is a single transition state. And I think catalysts actually have a more involved role than that in most cases. So if that were the case, then I might rather draw a picture that looks something like this. So again, here is the reaction without the catalyst, has the high activation energy barrier. And with the catalyst, it might have a different reaction mechanism that may have several transition states. And so again, it's going to be a lower overall activation barrier with the catalyst, but it's going to be a more interesting and more complex reaction that occurs with it. Now, I know that this looks imposing, that I'm going to put this big table up on the screen, but what I'm going to encourage you to do is to listen to what I have to say about it and then maybe take a screenshot of the table when I'm done, because it's going to summarize a lot of information about these three different types of catalysts. I'm going to describe essentially different steps that a catalyst might use in helping to facilitate a reaction. The preparation step, where they modify the reactants by the catalyst, an initiation step where they bring reactants together. Execution I won't have as much to say about because that varies from one catalyst to another, and it's really just where the reaction is happening. And then finally, the fourth step is a reconstitution, where we're going to restore the catalyst and we're going to release the products somehow to be on their own. And then I'll tell you in each case some types of reactions that these apply to. So let's talk about acid-base catalyzed reactions first. The first step is usually that the reactant is protonated or has a proton removed. That is, it undergoes some sort of proton transfer reaction, either by accepting a proton or by donating one. And that alters the reactant and allows it to undertake a reaction. The next step would be that the reactants would be induced to participate in this acid-base chemistry. That's the initiation of the reaction. Now the reaction will then take place, and the way it's reconstituted is that the initial acid-base chemistry, the proton transfer that happened at the beginning, is reversed now that we have products. Now this is the sort of step that often occurs in organic reactions. It happens in some inorganic reactions as well, used for synthesis. So this is a tool that chemists might use to make a molecule of a particular set of characteristics. What about metal surfaces? The first step in this case is that the reactant adsorbs on the metal surface. Now what does that fancy word mean, adsorb? It just means it sticks to the surface. Okay, so the reactant is going to come down, it's going to stick to the surface and stay there. Now reactants can diffuse on that surface, and this is what happens until they encounter one another. So in this way, the metal surface is providing a template on which the reaction can occur. Once the products have been formed, they can then unstick from the metal surface, or desorb, as we would say. So in this case, the metal surface has simply created a template on which the reaction can occur. And it's very good at doing this, and especially in many industrial cases. So this is often used for gas phase reactions. It could be used in the solution phase, but it's really key in a lot of industrial products. So for example, we've talked about the Haber process from time to time, and that is a classic industrial reaction that is catalyzed by a metal surface. Finally, enzymes involve the following set of steps. They start by binding the reactant to an active site on the enzyme. So the reactant might drift in. It's tailored to fit into a very particular place on the enzyme. There may be a metal present at that site that helps to bind it there, but the reactant sticks to the enzyme in a particular place on it. Another reactant molecule might then be brought into that active site while the first one is stuck there. Or it may be a decomposition reaction that takes place at that active site. But whatever happens, it's going to happen now at the active site of the enzyme. Once the products have been formed, once the reaction is done, the products will detach from that active site of the enzyme and be released into the cell. Now, of course, this is something that you'll always find in biological reactions, especially for essential cellular reactions. So this is a very quick roadmap on how to think about catalysis. And again, if you want to keep this table, you may want to make a screenshot of this chart, and then you can refer to it later.